Good morning, Professor. Here's my presentation on wind turbine power output forecasting using artificial intelligence. This paper was written fairly recently in about 2022, and I'll get right into it. So here's some background information. Increasing global concerns over climate change have forced mankind to shift from pollution-causing, exhaustible sources of energy to more reliable and more environmentally friendly renewable energy sources. Wind energy stands at the forefront of the transition to renewable sources, offering a clean, abundant, and sustainable alternative to fossil fuels. However, the inherent variability of wind speed and direction introduces significant challenges to accurately forecasting wind turbine power output, which is crucial for grid stability and energy management. Now, there are a lot of AI techniques like machine learning to help deal with this nonlinear data, using machine learning and deep learning for predicting these wind energy outputs. This goes straight into our problem statement, is wind turbine variability. And really the core challenge, I guess, tackled in this paper revolved around just wind, how it's unpredictable, how there could be windy days and there could be, days where there's not a lot of wind. And traditional forecastings methods using statistical methods have failed or struggled to accommodate the dynamic and mainly nonlinear characteristics of the wind speed and direction, which can lead to inaccuracies, which could cause power quality problems, can affect grid reliability and efficient energy distribution. As you can see, I showed kind of how a wind turbine works, just the rotor, hub blade, generator, driver train, tower. Sorry, I'm cutting it off in figure 1. And I've also shown relevant equations throughout the paper used to the power equation and the tip speed ratio equation. So the first kind of technique that the paper went into was the polynomial regression model. Now, if you look at it, I put in red. Under machine learning, there are many different types of machine learning. There's supervised, unsupervised, semi-supervised, reinforcement learning, and deep learning. And this polynomial regression is under the supervised learning. And the advantage of it is that it's very good for capturing nonlinear relationships between variables by fitting a nonlinear regression line, which is not possible with linear regression. So basically a nice line of best fit. And this is kind of how it works. It studies the problems, trains the machine learning algorithm through the data supplied, it evaluates the solution, and either chooses to launch or reanalyze the errors. Kind of like a nice little closed feedback loop, or open feedback loop rather. That was the first analysis technique. And the second analysis technique was deep learning using LSTM. And LSTM stands for long short-term memory. Now, the difference between this method and the other method is that it's two completely different categories of AI. This is more in the deep learning using a completely different algorithm than this. So how deep learning using long short-term memory works is by using recreational neural networks, RNNs for short, to predict the data. It's basically giving constant feedback in a long-term running loop. Now, RNN is for short-term memory, but LSTM basically converts it into long-term memory, which will kind of fit our need for the wind turbine as our application. Now you could kind of see how the system architecture works in this, and kind of how the feedback loop works in. It uses a lot of math and a lot of variables in order to solve it. So now we want to get into the data set. So this paper used 80% data to train and 20% for the rest for the data to predict. And it ran it on those two different models, the polynomial regression and the deep learning model. Now, the data set that the paper applied was from the National Institute of Wind Energy from a time span of 3 years with hourly recording, which had about 18,757 records. And the parameters of what the paper used were timestamp, the hours, days, month, and year, the wind speed in meters per second, and the wind direction, degrees, horizontal component, vertical component, LV active power. So these were all the parameters that the data set used. And this is important to keep these parameters low in order to, control the algorithms. So we'll go into the results of the first baseline model, and that was the polynomial regression, and this is the proposed model 1. So on the left-hand side, the figure below shows the scatter plot of the LV active power and the wind speed, two of the parameters in the data set. And he was able to find the mean absolute error in predicting the output power, which is 19.1 watts, which when you're dealing in kilowatts is very, very accurate. So as you can see, sorry, the images are a little bit blurry, but you kind of see how it kind of goes in this shape fashion. And there's some amounts of, outliers, but you could kind of get the general picture. And on the right-hand side, it shows a graphical comparison between the actual and predicted power, and this blue line depicts the true value. And the red line, which I have not shown, depicts the predicted value of power. I'd have you reference the paper to see that information. So now we go into the second results section. And on the left-hand side, you could see the wind speed shown by pie charts, along with the wind direction. This is more supplemental. On the right-hand side, you could see the graphical comparison of the true value and the predicted proposed model. I'm sorry it's a little bit grainy, but the true and the proposed, the true is the blue and the red is the proposed. So you could see how it very clearly kind of mirrors this, which is very nice. It shows that the model is really learning, and the results were very impressive. It showed an impressive accuracy of 96%. These outcomes not only highlight the effectiveness of AI in enhancing wind power predictability, but can also be applied as long as we keep the complexity low. So this is showing very good progress. Upon reading this paper, I had some questions for the author. Some maybe things were unclear when I was reading it than when I was analyzing it. The first thing that I kind of wanted to, look into more was why they used 80% data to train and 20% to predict. Maybe that's just like an empirical rule or a rule of thumb that I wanted to really understand. I'd really like if they would be able to, kind of see if the data set could get more accurate or less accurate, depending on if they went with 70% data, 85% data. It's obvious that, more data, less to predict will be more accurate, but maybe it's not as linear as we might expect. Maybe there's a best fit sweet spot. The second question I had was there any data pre-processing details? In the paper, he kind of said that cleaning has to be thoroughly done. I want to know how important this is to the process. And this kind of leads me into my next question, is the impact of data pre-processing on accuracy. If there was no cleaning of the data, how accurate would it get? in the long term. I want to thank you for listening, and I look forward to discussing this potentially in class. Thank you, Professor. Have a great day.